It's the next talk, don't worry. Okay, so this is a talk about, it's not really about effects as people usually understand them. This is about using effects to implement a programming language. And in a way, I mean, obviously there are programming languages that do type checking and elaboration, and this is just a typical programming language researcher way of rearranging the deck chairs to do something you already thought you could do already. And it's a bit like going to the supermarket where they've rearranged everything and they put the cat food next to the toilet roll. And you think, why did they do that? And this is just a different way of doing something you already know how to do. So let's write a type checker. And we're going to need some types. I apologize, I've used the kind of annoying Oxford style of writing up Haskell where you can't actually type it in. But it looks great on slides. So we've got some types, A, B, and C, and we've got function types, and then you can compare them. And we've got some terms, we've got variables, we've got lambdas, and we've got application. We're going to write a type checker for the simply type lambda calculus for this. So a type checker just takes a term and the list of types representing the context, just using De Bruyne indices to represent variables. And it either gives you back nothing, meaning type checking failed, or it gives you back the type of the term in that context. So this is fairly straightforward. We have variables, we just look them up in the context. This double bang notation is Haskell's thing for a lookup thing in a list by index. We type check lambdas by extending the context with the type of the bound variable, and then we type check the term. If it gives us back a type, then we create the function type. If it gives us back nothing because the body failed to type check, then we return nothing. And application is a little bit more complicated. We type check the function position part. We type check the term, the argument position part, and we check that the types all match up, and if they do, we return the result type, otherwise we return nothing. So let's take this type checker to bits. This is how we might implement the front end of a compiler. Let's take it to bits and see if we can put it back together in a nicer way. So we've got the same types, but now we're just going to forget about the terms for a bit, just forget terms. And we're going to say, what is a type checker? For us, a type checker is going to be something which takes a context and returns maybe a type, and nothing that means we failed to do type checking. And instead of having terms, we're going to sort of decompose the type checker into little bits of programs that have this type checker type. So a variable is a little type checker which just does what the variable case did in the previous slide. A lambda is something which just does what the previous one did on the previous lambda case did in the previous slide. And I apologize, there's a typo here, which I just realized should be a lambda context here, because otherwise it doesn't type check. And application, again, it takes two type checkers representing the two subterms, or result of type checking the two subterms, and it just passes the context through and that, checks the types, checks the function type, checks that the type of the argument matches the argument position of the function type, and returns the argument. So now we can go back to having terms, and we can now think of a type checker as just simply something which interprets terms. Like we can think of the program that the user has typed in is basically just a little program that we're using to run to script our type checker. And this idea of scripting a type checker is what I want to sort of push on here. So we're going to think about these as the sort of these are kind of effects that we're going to use for our little type checking engine, and then we can think about adding more effects to do new things. But before we can do that, we can sort of see how we can turn source terms into these little type checker scripts. So this lambda f, lambda a, fa is just lam, and then we have to annotate the type, lam a, and then apply, and we use De Bruyne indices to point back. Don't worry about De Bruyne indices, I'll get rid of them later. And also, because now we're talking about little type checker scripts, we can talk about, we have them inside Haskell, so we can talk about them as programs, and we can type check terms with holes in. So here we have a term which has a hole in, and which we just represent as a meta-level lambda abstraction. And as I said, we can now think about having yet more bits for our little type checking language. So we can stick with our same type checker type here, but we can now represent failure as a first-class thing. So we can start to write type checker scripts which have the possibility of failure. So by itself, this doesn't seem very useful, but we can use it later on to represent sort of conditional and backtracking. We might want to also let the typechecker script inspect its environment. We can let it see what the variables are in scope. So I have this have thing, which given a number representing a bound variable and a type, all it does is check the context for that variable. If it has the right type, then it just carries on as before, otherwise it fails. So we can put assertions into our typechecker scripts to say, I'm expecting that variable X, or 2 maybe, has the right type. And we can sort of pin it down. And one thing here, I think this sort of is going to come more apparent later on, is that typechecking is sort of, we're typechecking functional languages, but when you think about how the typechecker runs through the term, there's almost a kind of imperative thing going on. It's updating the context and adding things, we go into new scopes, sort of stack allocation. And this lets you put asserts in. I mean, imperative programmers used asserts for years and years and years, but we haven't really been able to put asserts into our functional programs to say what I think this variable has types. You have to sort of fake it by having a little dummy let or something. And we can also, as well as saying what the type of variable has, we can say that the whole term has some type. So it's expecting that the thing type-checked from this type-checker has this type, and it just runs the type-checker on the subterm, or the sub-type-checker, and asserts that the two types are equal and fails otherwise. So now we can write terms which have assertions, and this is sort of not very readable, but it will become more readable later on. But we can assert that this term here, which was the lambda f, lambda a, fa from before, has type a to b to a to b. And the one with the hole in, we can wrap it in an assertion that says what we're expecting, dynamically what we're expecting the type to be. And we can have two assertions. So here this is just a completely pointless assertion which just asserts that this lambda here has type a arrow b. Or now we're asserting because 1, that's 0, that's 1, points to just asserting that the variable bound by that lambda has type a arrow b. So we've got this kind of carrier thing, which was list of type to maybe type, and we've got a bunch of operations. We can start to think about, well, that's starting to look a bit like an algebra. We can start to think about, like, we don't have to have that implementation. We can have other implementations, we can have other ways of thinking about it, and we can think about what equations hold between terms in this thing. If we got these little typechecker scripts, then when are two typechecker scripts equal? When is it safe to refactor the typechecker script or proof script or something like that, and still mean it's going to come out with the same terms in the end? So these are the operations. There's the three operations here that actually build terms, and there's the three sort of commentary ones, the ones that sort of just talk about the terms as they're being built. And the first set of equations is kind of straightforward. Just failure is contagious. If failure happens anywhere in the type checking process, then it bubbles all the way up to the top, and the whole process fails. And you could think of a more user-friendly one of this, which as the failure is bubbling up towards the top, it starts to add error messages to talk about the provenance of where that happened in the term. The second set of equations deals with this have operation. And where this is most interesting is around lambdas. So if we just have a bare lambda like this, then that's equivalent from the point of view of being a type checker to saying that the new bound variable, so have 0, has the type bound by this lambda abstraction. And also if we make an assertion outside a lambda abstraction and we move it inside the lambda abstraction, then we just add 1 to the De Broglie index. And then for the rest of them, so have just commutes with application. And when we have a have which hits a variable and it has the same index, then that turns into a has type, because now this term will have the type A, assuming that the variable that was being used has the type A. And if we make the same assertion twice, then that's the same as doing it once. If we make two contradictory assertions about the same type, then this is failure. Some people may be worried about the use of negatives here in an algebraic theory, but it's okay because there's countably many types, and you can just assert lots of equations. And we can commute to have assertions if they're talking about different De Broglie indices. Now, and the last set of equations is for has type. So this is sort of the kind of the dual to have, in not a very formal sense. If a lambda abstraction and the body has type B, then that sort of bubbles up out, and we now say the whole thing has type A arrow B. If in an application, if the left-hand side has type A arrow B and the right-hand side has type A, then the whole thing has type B. We have to leave in this assertion here in order to sort of match up the possibility of failure on both sides. Because there's a hidden type inside the application, which is the type of the argument. If we try and assert that the argument position in an application doesn't have a function type, then we fail. If we try and assert that the argument type doesn't match in an application, then we fail. Has types, if we assert that the term has the same type twice, then it's okay. And if we assert that it has two different types, then we fail. And actually, from this equational theory, we can prove that it sort of matches up very closely with type checking. So I have this theorem that if a term A has type, term T has type A, if and only if we make this assertion and then we translate this term into just the var, lam, and app construct terms effect, then it won't be failure in the type checker theory. But this is about effects, and I haven't really mentioned effects. Well, sorry, this workshop is about effects, and I haven't mentioned effects yet. But we have an algebraic theory. So what do we have then? If we have an algebraic theory, we have a monad. So all I've done here is take the operations I mentioned earlier, the var, lam, and app has type and failure, and just sort of seen them as the operations in this free monad. And this is just the bind here of the free monad. Really, it's taking these trees of operations and doing substitution. And now we can start to write typechecker scripts which look a bit more like tactic scripts that you might see in a tactical theorem prover like Coq. So we can sort of make some shorthands here to make these scripts a bit nicer to write. So var I is just capital var I, but lambdas we just return in here, and we're going to use the bind to actually put bodies inside lambdas. And now we can start to write scripts which look like this, which are now starting to look a bit like you might write tactic scripts in Coq or Isabel. And I've written goal is rather than has type to try and give this idea of kind of doing proof search. But so, well, we're going to assert that the goal is to prove that A implies B implies that A implies B. I'm going to do this by doing a lambda abstraction, another lambda abstraction. I don't want the reader to get lost now, so I'm going to assert that I've done one step ago, I did a lambda abstraction which did A arrow B, and I did a lambda abstraction which did A, and reassert that the goal is B. And then I'm going to conclude by saying, well, we can prove B by applying var 1 to var 0. So,
excuse me.
Yeah.
Can you go back to the previous slide? So lambda, TCTerm, and then the next slide. I'm just trying to understand the lam A equals lam A return unit. Like why there? So is there still a bound variable after that, or a meta language?
Yes, yeah, so I'm just going to talk about this. So I've been very sloppy so far with what the bound variables are. So you have to make sure that you do use the numbers correctly here, otherwise the whole thing just breaks. So the very next slide is going to be two ways of fixing that. But good question, though, yes. Right. So yes, I've been extremely sloppy. And there's two ways of fixing the scoping issue. One is to explicitly type things with De Bruijn indexes. So here, this type checker class is now parameterized by the number of free variables that we have. And we now, when we use variable, we have to make sure we have this fin n, which just means any number less than n, type of numbers less than n. And we get a term which is well typed, well scoped in n variables. And when we do have, we make sure that we're only referring to variables which have already been declared. And when we go inside a lambda, we sort of go up one level with the suck operation. And this is based on the abstract syntax and variable binding by Fiore, Plotkin, and Turi from Lex 1999, where they talk about algebras for the untyped lambda calculus, algebraic theories of the untyped lambda calculus. I have these operations, and all I'm doing here is adding these extra operations that we can use them to talk about type checking. However, when you actually write these things, it's incredibly bureaucratic, where it's constantly shifting things and worrying about numbers. So a nicer way of presenting this is to use higher order abstract syntax, where we parameterize the typechecker type class by this extra, it's a new, but it's V for variables. And so this represents this sort of abstract pointers back into the environment. And due to the magic of parametricity, we can always be sure that whenever we use one of these news, because the only way of getting a new one is this lambda thing, we can always be sure that we'll always be well scoped. And type checkers with no free variables are represented by this type. So this is a type class constraint here. And this always makes sure that we don't have any, because you can't get a new, the only way of getting a new is to do a lambda, you can always be sure that the terms are closed. So now this is the same free monad, but now expressed using this higher order abstract syntax. So now, rather than there being this implicit, we've got an extra variable here, lambda now takes a function which will be the representative or pointer back to that variable. And now the bind is almost the same, except we have to do the only thing you can do here in the lambda case. But now we can write scripts where instead of implicitly referring to variables via numbers, we can refer to them by symbolic names. So now this is the same script as before, but now when we do a lambda abstraction, we call that variable v1. We do a lambda abstraction, we call that variable v2. And now we can assert that v1 has type A arrow B, and we didn't have to count back through the lambda abstractions. We can assert that variable v2 has type A, and we can now assert the goal is B and apply v1 to v2. Now, we don't have to write lambda. We can start to make this look a bit more like Coq, which is some sort of trivial rewritings. We can just say we're introducing a new variable called v1, which has type A arrow B. We're introducing a new variable v2, which has type A, and we don't have to write var at the bottom. We can write assumption. And now it just sort of starts to look more and more like a kind of tactic script, except it's a bit more principled than the tactic scripts that you get in Coq or Isabelle, where it's essentially a dynamically typed programming language. Now it's a kind of algebraic theory that we can reason about. We know that if we swap these two lines, then we get exactly the same proof terms coming out because of the equations in the algebraic theory. So I started at the start by saying that there was this concrete type checker implementation, then I went all abstract by saying we just have this type class in the equations. But now when we evaluate type checker scripts, we've got several different choices. So the first one is that we can just do type checking. So this evaluation, all it does is replay the commands from our free monad in the type checker, anything which implements the type checker type class. And the first one is we can just do type checking, but we can also do elaboration, where we build a type check term through the process of running one of these type checker scripts. So this is a kind of fake dependent type notation, but it's given a context, which is a list of types. So I'm being very sloppy here with scoping again. Then it maybe gives us back the type of the term and a constructed well-typed term represented by this index type here. We can also start to think about variations of this scheme. So one useful technique for implementing sort of complex type systems is to use bidirectional type checking. So before, I had to put sort of annotations on all the lambda abstractions, which is a bit tedious. But to avoid that, here there's lam has no type annotation. You can sort of do this bidirectional scheme where you push types into terms in normal form, beta normal form, and you extract types out of neutral terms. So I'm going to call those two phases, checking and synthesis. And we have, so for the variables, then a variable can synthesize its own type because it can get it from the context. A lambda abstraction, it's going to check its own type, so it's going to have a type pushed into it, so it can see that it's A arrow B or something like that. So then it can extend the context with A, and then it can check that the body has type B. Application, the head term has to synthesize a function type, but then the argument term gets checked against that type. We can switch from synthesis to checking And that means a type is going to be pushed in and a type is going to be pushed out, and we just have to check that they're the same. And we can ascribe types. So this is all the kind of syntax part of the thing. And now we have the three operations again. That's that kind of comment on the type checking process. So now have is polymorphic in which direction you're going. You can always make assertions about the context. But goal is we're type checking against some type, but we can only do that when we're in the checking phase. If we're synthesizing a type, we can't check what the current goal is. And failure is polymorphic. We can fail anywhere. And here's sort of yet more fake dependent type notation. And yeah, so a type checker, which is in checking phase, takes a context and the type to assert that it is, and returns a Boolean whether it's failed or not. And in synthesis phase, it's like it was before. It takes the context and a maybe type to check it against. So this means that because we're pushing types in, we have this expectation of what's going to happen. We can write these sort of programs or type checker scripts or source level terms which are active in their environment. So we no longer have to put annotations on this introduction to do lambda abstractions. We can just do two lambda abstractions. Then we can say, well, what type do I need to be? And let's say it was type A, then I can be some type A constant. Some term, some A constant. If it was type B, I can be some B constant. Otherwise, I can just refer back to this one. So we have terms which are kind of active in their environment. They don't know what type they're going to be expected to be, but they can be type checked nevertheless. So this sounds like it might be a bit sloppy, but there's this nice paper from eCoop last year, safely composable type-specific languages, where they use this kind of power to be able to have custom facilities for having literals within the programming language. So you have a string or something which is in the programming language, and you don't know whether to interpret that string as a bit of HTML or a bit of SQL or something like that. But the type checker in their system can ask, well, what type am I expected to be? And then it can interpret this string as an A constant or HTML, or it can interpret it as a B constant or SQL or something like that. So you have the interplay between the type checker and the term itself. So the terms are kind of active. Another nice variant of sort of treating type checkers as effectful computation is an adaptation of this other nice paper by Sam Staten, an algebraic presentation of predicate logic, where he uses this formalism of algebraic effects with name generation to give a kind of algebraic representation of Prolog. So I'm going to extend the type language now with metavariables over some type mu. So this is going to do a kind of Hindley-Milner style type inference. And again, we have var, lam, and app. Notice now that the lam doesn't have any type annotation as before. And we can add two new operations that create a new metavariable and unify two metavariables. We can change have now, rather than making an assertion about any particular variable in context, we can just ask for the entire context. This is orthogonal, really, to the inference thing here. We can say, ask what the goal is again. And we have a failure again, but now we also have a choice. So we have this kind of Prolog style backtracking. We can have a guess at something the term is going to work for. We can the term can, again, sort of inspect what the type is. It can fail. If it doesn't work, we can backtrack and try something else. And here's a type of what an implementation of this would be. It takes some meta context, which includes all the type variables which have been allocated so far, substitution, and the context and what the goal is meant to be, and returns yes or no whether we've actually managed to satisfy all the constraints. So using this, we can sort of write a little by-assumption tactic for programming. So we might have some point where we just need something of the right type, but we don't want to bother having to say what the variable name is, so we can sort of write in our meta language a thing which gets the current goal, so that gets the type as expected to be, but this could just be a meta variable. Gets the current context, so in this system it just gets all of the variables in the context. And then we just do a sort of search down the list. I've missed a bracket here. And if we get to the end, we fail. Either we try and unify with that variable in the context, the goal with the variable in the context, or we can go on and search further down the context. Yeah.
So should, in this instance, should it also be returning sort of the new state of the meta variables, or?
So that's implicit in the in this type down here. It should be implicit in this type down here. This should return a maybe meta context. Yes. Okay, fine, yeah. Fine. I have to come clean here. I have written all this in Haskell on the slides. The implementation is an OCaml. Because, yeah, I don't know. Yes, so this would do the unification, returns the new meta context, and returns, or it carries on searching if that choice didn't work out. And yeah, we search down the context and return that variable. So this is the end. So the summary of this is, I think it's a nice idea to treat the bits of a type checker as operations, rather than having a great big monolithic type checker, which is some enormous match statement or case statement, depending on the language. You split it up into operations, and then you can let the user script that in order to give a more powerful way of writing programs. And also it works for elaboration. So my main motivation for this was to try and understand elaboration in independently typed languages. And there we want a sort of rich source language which compiles down through the front end into a sort of nice a sort of core language. And this was our way to try and understand that and understand the different ways that you might try and get rid of sort of things like pattern matching and turn them into eliminators and things like that. But one nice thing is that you have this kind of active terms which can sort of respond to their environment and do the right thing, which I think is a nice thing that could be explored and has already been explored in that EQ paper. But does this work for more complex type systems? I don't really know. What are the right operations and equations in general? It might be argued that I just pulled a rabbit out of the hat when I said we have has, type, have, and failure. Why? Why did I do that? What are the free algebras for the type checking monad with the equations? Is this a sensible way to actually do things? I mean, obviously we all have type languages. They are implemented. Why change? What is the relationship to tactic scripts or high proofs or eval mode or anything like that? And does this subsume hygienic macros? We have these kind of scripts which can write bits of program for us, and using the higher order abstract syntax, they're guaranteed to be well scoped. Do we get a kind of macro system there as well, which can also look at the types which are being pushed in and pulled out at the same time? That's everything. Thank you.
Do you know how this might relate to Bauer's Andromeda?
No. The extensional type theory checker.
It's kind of like it's trying to write backwards.
Yeah.
Checking with effects and handlers.
I don't know.
Can you comment on how this relates to Type's final interpretation?
It's very similar. So if I go back to the, well, you can see it here. And so this kind of abstraction here is the same kind of higher order abstract syntax approach that they use there. So this is, rather than in the finalist tagless, finally tagless approach, where they make you use the meta level type checker to type check the terms. This is using the meta level type checker to make sure the terms are well scoped, but we're actually just writing the type checker itself.
This is sort of an observation that Martin Loff's presentation of dependent type theory has a very algebraic flavor to it already. And it would be quite interesting to explore extending this with a couple extra judgments. In particular, you know, equal as types, which is close to sort of unified, but to have an explicit equal as types judgment. And then if you add, you know, terms are equal as values at a type, then, you know, you might sort of be able to level this up to proof scripts that would, you know, really give you the power of sort of a Coq-style language, and that would be really neat.
Yeah. But I think some of the work that Marcelo Fiore has done on algebraic theories for these kind of much higher typed languages is relevant there too.
So you said this was done sort of in the context of, you know, exploring a way to make a pattern to eliminators for dependent types compiler. Have you done that application?
No.
Versus-
I have done it with pencil and paper, and then just scribbled the bits that didn't work. So yeah.
Okay, let's move on. Thanks, Bob.
Okay, hello, thanks for having me. How do I press the... Ooh, no, that's not good.